we've heard a lot of presentations about VPP and how great it is, how fast it is. But we haven't really heard anything about Kubernetes so far. And I guess we are at KubeCon, right? So maybe try to see how we can integrate this great technology with Kubernetes. And from my experience, it was something like that, where everything was a mess. And then, at the end, I guess it worked out. But today, we're going to speak about Kubernetes services and Kubernetes policies. This is the agenda for today. So I'm going to go through a brief overview of what Kubernetes services and Kubernetes policies are, and then how we implemented that in VPP, or actually what features of VPP we used to implement the control plane for Kubernetes services and Kubernetes policies. And then if I have time, I might go through some packet flow examples. So how many of you have actually created the Kubernetes service? 1, 2, OK. And pretty much Kubernetes service is an abstraction which defines a logical set of pods and the policy by which to access them. So you can think of a Kubernetes policy as a dynamic load balancer, pretty much. So these set of pods are targeted by a service, are usually determined by a label selector. And then we have this query that matches those pods that have been created from Kubernetes previously. Now, a Kubernetes service can be published to the cluster or to the outside world in 3 different ways. So we have the cluster IP, which exposes the service on a cluster internal IP. We have the node port, which exposes the service on every node's host IP address with a specific port from a predetermined range. And then we have external IPs, which has an unlimited number of cluster outside IP addresses that should be routed to 1 or more cluster nodes. And then from there, they get load balanced across services and endpoints. Now, the difference between a typical CNI implementation and Contiv.VPP, which is another CNI implementation, is the use of Kubernetes Proxy. So in every other Kubernetes CNIs right now that are available, they pretty much use Kubernetes Proxy to do services. And Kubernetes Proxy is fine, but it's not as fast as doing nothing inside VPP. In Contiv, we use VPP as a vSwitch in every node. It's a pure user space implementation, of course, and we use load balancing and translations between services and endpoints using the NAT4 plugin. So this is the first thing we leveraged from VPP to implement services in Contiv. Of course, we have an exception where the traffic gets initiated from the host, and that's where we still use Kubernetes Proxy. Right, so from the VPP's NAT plugin, we use the implementation of NAT44 and NAT64, and we leverage 2 modes of that NAT plugin. The first mode is the load balance and forward IPv4 traffic between services and endpoints. And then, in example, this is one-to-many NAT. And then the second mode is a dynamic source-NAT for the node-outbound IPv4 traffic. So when we want to enable internet access from pods that have a private IP address to the outside world. Now, for the one-to-many NAT, what means in VPP is a collection pretty much of static mappings. And each static mapping consists of one external IP address port, endpoint, and then multiple weighted local endpoints. And on the right-hand side, you can see the VPP API definition. And what's interesting here is that to fully support NATing in the Contiv and Kubernetes environment, we had to add a special feature for Contiv, which is the self-twice NAT. That happened because we had the case where endpoints that were behind the service wanted to reach the same service, right? So they were trying to pretty much hit the same endpoint as the request that you were originated from. So you would get the same destination address. Now, for that reason, the source destination and the destination IP are equal after the DNAT. So we had to do something to pretty much solve this problem. And we called it self-twice-NAT. That tells the NAT plugin to also translate the source with a selected IP address that will be routed through VPP. And that was actually the addition of the NAT plugin inside VPP to support services. We also use a dynamic SNAT. So for a dynamic SNAT of the outbound traffic, an interface needs to be put in the post-routing mode. And that's the VPP command where you pretty much set, normally that's the gigabit Ethernet, because that reaches out the internet. And the dynamic NAT also requires a non-empty pool of IP address to choose from for translations. And normally that's the node IP address. We also had to use identity mappings. That was for cases where a static NAT mapping lets a real address translate to itself. And I'll explain to you why we use that. And also we had to pretty much all the interfaces, we had to classify them as out or in, depending on what feature they were doing. So if it was a client where traffic gets connected to a service, that was an out interface. Whereas if it was connected, it was an endpoint that was connected to VPP to provide a service, that was an in interface. So that was on the VPP side part. On the Contiv.VPP, which is the control plane, a service is implemented as a set of VPP-NAT static mappings, one for every external address. Now, static mappings of a single service are grouped together, and from that, we form a single instance of a DNAT model, which is a proto-model in the control planes world. And that gets pushed to Legato, which is the control plane agent, and then through Legato, we configure VPP through the binary API. Now, every DNAT instance has a unique name to get identified, and it gets prefixed with the service name and the service namespace. I don't know how many things you can see from that, but this is pretty much the, let me see. That is the algorithm we use. This is a pseudocode, it's not the exact algorithm, to pretty much transfer the service to this DNAT mapping. So we have this input, which is the Kubernetes service, and the output, which is the DNAT configuration, which is going to get pushed to Legato. And what we do is we pretty much get all the endpoints of the service, and then we add these endpoints to the local endpoints array, and with a specific probability. And then depending on if we have a cluster IP mode or a node port mode or an external IP mode, we calculate the mappings that are going to be installed in VPP. The next thing we need to do is to mark interfaces, like I said, with in and out features, so that VPP-NAT plugin can understand the direction in which the NAT should be applied. So in the nodes interfaces, connecting service endpoints with VPP, and then out the nodes interfaces through which clients can access that service. Then we need to mark the gig Ethernet interface that connects VPP to the default gateway as output, which is the routing mode that we said about gig Ethernet, and add the node IP into the NAT main address pool. And then the last thing is that since we did not desire the source-NAT packets sent internally between nodes through VXLAN encapsulation, we need to exclude from NAT using an identity mapping. So it's what we did with mapping the same real IP address to itself for the VXLANs. And this is the architecture that we use inside the agent. So on the top, I don't know if you guys can see, is the Kubernetes master API. So through the Kubernetes master API, we push down configuration for Kubernetes services. And then we have something called KSR, which stands for Kubernetes State Reflector, and takes all that state from the Kubernetes master API and replicates that in our own instance of database, which is etcd. Now, from that point on, because we did that because we didn't really want to touch Kubernetes database, and we wanted to maintain our own state, we have this Contiv.VPP agent plugin, which follows a data flow model. So on top, we have the skeleton plugin, which listens to etcd, to our own instance of etcd for changes in Kubernetes services or Kubernetes pods or Kubernetes namespaces. So every time we add a service or every time we add a pod or a namespace or something like that that's of interest, then the service policy skeleton plugin will grab that change. And what essentially happens is that it pushes that information down to the processor. And then, if I actually move one slide here, the service processor, and then from the service processor, we can use the renderers, which can be different renderers for different data planes. So that architecture supports multiple data planes. So it can be VPP, but it can be anything else that, you can take that abstract 6-tuple that the processor generates and then push it down to any data plane. So the service plugin skeleton is responsible for the layer initialization, and it has an etcd watcher that, like we said, then propagates changes to processor. The service processor unpacks those data changes and matches those service metadata with endpoints. So it's trying to find all the pods that match the label selectors of the service. And then that outputs all the pre-processed service data to the renderer layer. And what essentially happens also here is that we have front-end and back-end. And front-end is for pretty much all the pods that they don't run behind the service, whereas back-end is all the, let's say, interfaces that are potentially going to run a service or connect to a service. And all that information is getting sent to the NAT44 renderer, where it maps that Contiv service data that it receives from the processor into a protobuf model, which is essentially the configuration that gets pushed down to VPP. Now, the renderer also is responsible to do the mapping between front-end, well, classifies the front-ends and back-ends without and in interfaces, identity interfaces, and then the management of the dynamic source-NAT for node-outbound traffic is configured to enable internet access for the pods, again, through the renderer. And this is how the configuration looks like. So as you can see, we have 4 pods that run behind the service. And the pod 1 actually is a client. So it's classified as, its interface is classified as out, whereas tab 2, tab 3, and tab 4, they are both out and in because they are connected to VPP to provide the service, but they can also act as clients. Same thing for tab 0, loopback 0, and then if you see gigabit Ethernet is marked as output, so it can provide the connectivity to the outside when we do the dynamic source NATing. Another problem we faced with Kubernetes services is that the network policies, they run below the network services. So that means that destination address translation needs to happen before the ACLs are applied. And the VPP guarantees that the following ordering between the ACL and the NAT44 rules are executed in VPP. So you have first ingress ACL, then you have destination NAT, then you have your routing and switching, then you have egress ACL, and then you have your dynamic SNAT. And that means that ingress ACLs, they cannot be eligible for policy implementation. And we can show later on how we solve that problem. I have 5 more minutes, so I'll try to be fast. The next is Kubernetes policies. So Kubernetes network policies define how groups of pods are allowed to communicate between each other. And each policy is represented from a Kubernetes network policy, which is another resource of Kubernetes. Again, other CNI implementations, not all of them, they implement a Kubernetes native CNI implementation, Kubernetes network policy implementation, whereas VPP and Contiv.VPP has native support for Kubernetes policies. It's a pure, again, user space implementation. It tackles inside VPP, leveraging the ACL plugin. It can also, again, we follow the same architecture, the data flow layering data model, where we can support multiple data paths. And essentially what happens is we create these basic 6 tuple rules with destination port IP, source port IP, action, and rules. And then we push that down to the data plane. Or for the VPP stack of that Florian has been developing, we use these layer 4 session rules. Whereas in other CNI implementations, they use IP tables or IP sets to increase performance. And Cilium, I think, uses BPF, and it has more complex rules. Yeah, I think I said that. Here again, you can see, like I said, we follow the same architecture, where you have your Kubernetes master pushing down a Kubernetes network policy, and that gets reflected to the data store. And then we have the policy plugin listening for those changes. Now, the difference is that all the changes we have from the etcd data store, we store them in cache. So we have some hashing mechanisms, and I think they are called IDX mappings, that they provide some fast lookups. And pretty much we want to have that for faster lookups and to store all the information in our cache that all the layers can actually access, so we don't have to overload transactions in the data store. Policy plugin skeleton, again, it initializes the layers. It has an etcd watcher, and it updates and resyncs. It's responsible for updates and resyncs. The cache unpacks all these data changes and stores in memory and provide callbacks to watchers. So now we have watchers in cache that, again, listen for changes when we add the pod or when we add a namespace, when we add a policy. And that's processor that implements that, pretty much that policy cache watcher. And what essentially the processor does is when it sees a change, then it calculates the set of policies currently assigned to a pod. So if we add a pod, then it will calculate all the policies applied to the pod based on the label selectors. Or if we add a policy, then the processor is responsible to find all the pods that are affected from that addition of policy. So we create these policies to a less abstract Contiv policy, which pretty much includes all the pods that have been affected, all the policies that have been installed, or all the policies that have been affected. And then we push that down to the configurator, which translates this Contiv policy into, again, a semantically equivalent set of 6 tuple. And this is where you can pretty much split into egress and egress side from VPP vSwitch side of you, because egress and ingress and egress in VPP world is different than ingress. Actually, it's the opposite than ingress and egress in Kubernetes policies. Configurator does that pretty much mapping as well. And then that set of basic 6-tuple rules gets pushed to different renderers. So we can pretty much attach different renderers to the configurator that gets those rules, and then we apply that configuration to whatever data plane we have underneath. And that's just more details, I guess. I won't have to dig into this. I'm out of time. Yeah, it's just pretty much more details of how the layers work.
All right, cool. So we are a little bit behind schedule, but we will take time for, once again, one question. Yes.
Can you please explain your plan for BGP support in the future?
So the plan is starting next month. We will have this, well, it's an enhancement of VPP, Contiv.VPP, that will support BGP for propagating IP addresses towards the nodes. So I think it's
soon,
maybe the next 3-4 months.
How about IPAM? Does Contiv use your own IPAM or Contiv using the host local?
Contiv has its own IPAM allocation agent inside. It runs, I think, as in a pod.
Okay.